Okay, this is the first part of lesson 5.3, and this is an example of graphing a rational function. We've done a full example of graphing a rational function already, but it was for a reciprocal function. And we did it by graphing using the key features. This one steps it up a little bit. Instead of having the numerator just the number 1, we actually have a polynomial as our numerator. And we're going to go through the whole process just like we did through that reciprocal function question, and we'll look for all the key features. So to brainstorm, what are those key features that we need to determine when we're looking at how to graph a rational function? Well, the first one is we need to ask ourselves, where are the asymptotes? And by asymptotes, I mean, what discontinuities do we have? Because we know that other than asymptotes, we could have a hole. So asymptotes are holes. Do we have a vertical asymptote? Do we have a horizontal asymptote? Or maybe even an oblique asymptote of some sort? Once we've figured out our discontinuities, we need to look for intercepts. Where are x-intercepts? Whoa, x-intercepts. And what about a y-intercept? Intercept, not intercepts. So asymptotes, holes, x-intercepts, y-intercepts. We also need all of our behaviors. Not end behaviors, but behaviors around asymptotes. So we know we're going to approach asymptotes, but are we going to approach from the left or right? And when we do we go up? Do we go down? Do we level off at a number, like for a horizontal asymptote? Or if it's oblique, are we approaching from above or below? And are we going up with that asymptote, or are we following that asymptote down? Any others? Well, domain and range are sometimes useful. Not necessary for sketching. Intervals of increase or decrease. Or intervals of where the function's positive and negative. Don't necessarily need those ones to sketch, but useful nonetheless. What we do need, though, is we definitely need asymptotes, holes, x-intercept, y-intercepts, and behaviors. So that's what we're going to do when I say a full analysis using the key features. So let's look at our rational and let's keep those key features in mind. And as we pick parts out, we'll add to our sketch. So let's start by looking at our rational function. Our rational function is x plus 1 over 3x minus 6. Any rational function, we want to start by factoring. So we want to look at that numerator and denominator and factor fully. Is there any factoring to do on the top? No. Is there any factoring to do on the bottom? Yes. It might not think so because it's not quadratic, but we actually have a common factor. So we're going to common factor. Why would we common factor? Well, we want a common factor to see if we have a factor that's common to both top and bottom after we factor fully. So let's start by factoring. Factoring f of x. So that's x plus 1 over 3x minus 6. If we factor the bottom by pulling out that common factor of 3, and we're left with x plus 1, we have a common factor on top and bottom, so we'd have a hole. We don't in this case, so we don't have a hole. So that's something that we can tell right off the bat. No hole. So since we don't have a hole, what we do have then is a restriction on the denominator. Our restriction is that x cannot equal 2. And since that restriction doesn't divide away, we have a vertical asymptote. Our vertical asymptote says take the denominator, set it equal to 0. So take 3x minus 2, set it equal to 0 and solve. Divide both sides by 3, we get x minus 2 equals 0. So add 2 to both sides, we get x equals 2. So we have a vertical asymptote at x equals 2. And that discontinuity from the denominator tells us that. Since it doesn't divide away and it remains, it becomes your vertical asymptote. So I'm going to go all the way down to the bottom right-hand corner of my page, and that's where I'm going to start my sketch. So for our full sketches, we need an approximate scale, and we just need to sketch the key features. So if I put my 2 here, my vertical asymptote of x equals 2, we want everything on that x scale to be proportional to that being 2. So that would mean 1 would be in the middle, and double the difference away, that'd be 4, and we want to keep that in proportion when we're coming up with our sketch. But so far, just the vertical asymptote. All right, so we've analyzed, we've looked for one asymptote. Next question is, do we have a horizontal or an oblique asymptote? In yesterday's lesson, we discovered, or I told you, that when the degree of the denominator, by comparing the degree of the numerator and denominator, we can decide whether we have a horizontal or an oblique asymptote. And in this case, we have a degree 1 on the top and a degree 1 on the bottom, so that means our degree top and bottom are equal, therefore we have a horizontal asymptote. To find the equation of our horizontal asymptote, we look at the ratio of the x terms. So that means that, well, we have our function f of x. Ratio of our x terms, we've got 1x over 3x. So that ratio of our coefficients on x are 1 over 3. So that means our f of x is going to equal 1 over 3. And that is going to be our horizontal asymptote. Because the degrees are equal, we're going to, as x gets really, really big, level out around 1/3. And I'm going to prove that to you when we look at our analysis, or we look at our behaviors around our horizontal asymptote. So let's graph that horizontal asymptote. At 1/3, I'm going to make my 1/3 here. So that would mean 3 times that would be 1. So my 1 is going to be actually way up here. That's our 1/3. This is our f of x equals 1/3. That's my horizontal asymptote. Remember, asymptotes are designated with dashed lines, not solid lines. All right, 2 parts. Since we have a horizontal asymptote, we do not have an oblique asymptote. We don't ever have both, one or the other. So that takes care of asymptotes. We have a vertical, we have a horizontal, therefore we don't have an oblique. We didn't have any holes because we didn't have a term that divided out. That takes care of all of our discontinuities. Let's look at x-intercepts and y-intercepts, and then we'll look at our behaviors. X-intercepts. How do we find an x-intercept? Well, an x-intercept occurs when the function equals 0. So if we want to find the x-intercept, we would say, what is x when 0 equals x plus 1 over 3x minus 6? And if we multiply both sides by the denominator, 0 times 3x minus 6 is just 0, and that leaves us with just the numerator. So what that tells us is that when we're looking for x-intercepts, we're really just looking for the factors in the numerator. Or sorry, not the factors in the numerator, the roots from the numerator. When we were looking for vertical asymptotes, we looked for the root of the denominator. So the numerator tells us our x-intercepts, the denominator tells us our vertical asymptote. Something key that we should remember. If we solve this, we get x equals -1. Therefore, -1 comma 0 is our x-intercept. And we can add that to our graph. Keeping in mind our scale, I would put -1 right about there. There's our x-intercept. To find our y-intercept, our y-intercept occurs when the function equals, or sorry, not when the function equals 0, the function at 0. So when x is 0, what's y? Well, let's replace all of our x's with 0. We'd have 0 plus 1 over 3 times 0 plus, not plus, minus 6. And that just comes from our original equation, replacing x with 0. Now if we start to simplify, we would have 1 over -6. So the function at 0 is -1/6. Therefore, 0 comma -1/6 is our y-intercept. And let's put that, a third was here, so we go about halfway. There's our negative 1/6. So we're starting to piece together a graph here. We've got our x-intercept, we've got our y-intercept, we've got our vertical asymptote, we've got our horizontal asymptote. Let's look for our behaviors. How do we find behaviors around our vertical asymptote? Well, we have to do a couple things. We have to look as x approaches our vertical asymptote from the left side. So as we approach from the left side, where's our graph going? Is it going up or is it going down? And since we already have part of our function in this quadrant, we might assume that the graph is going to go down. And we can test that by picking a number slightly to the left of 2, plugging it in, and seeing what we come up with. What does our function do? Well, a number slightly less than 2 would be 1.99. If I plug 1.99 into our original function, we get a value that is negative. And that tells us that our function must be going down. Sorry, let me graph that on here. That means our function must be going down and approaching negative infinity. So as f of x approaches 2 from the left, we're going down, which means we have a behavior that looks like that. So we can start to connect our graph and show that we're going to approach our asymptote and bend down. What about as we approach 2 from the right? Well, if I put in a number slightly over 2, like 2.01, we get a number that's positive, which tells us that we're going to approach infinity and go up on this side, which means we're going to go like this. We're going to approach this asymptote and go up. Since graphs approach asymptotes, and since when we plug in a number slightly over 2, like 2.01, and we get a positive number, we know we're going to approach that asymptote and go up. Now the question is, what happens when we approach our horizontal asymptote? Well, this one might require a little bit of a test. Remember when I said I was going to prove to you that it was 1/3? Well, here it is. If we're looking for our horizontal asymptote, we're looking for when x approaches infinity, what's happening to f of x? Well, we determined that it's going to approach a third, but is it going to approach a third from above or below? That's really important. Same with when it approaches negative infinity. Is it going to approach a third from above or below? And we can determine that by plugging in numbers that approach infinity, like 1,000 and 1,000,000. So here we go. I'm going to create a nice little table here. X and f of x. If I plug in 1,000, what do I get? And if I plug in 1,000,000, what do I get? If I plug in 1,000 to our original function, I get 0.334, which is slightly bigger than 0.333, which is what a third is. If I plug in 1,000,000, I get 0.33334, which again is slightly bigger than a third. So as x approaches infinity, or as x gets really, really big, we approach f of x, or we approach a third from above, slightly bigger. On our graph, what would that look like? Well, infinity is in this direction, and as I approach infinity, we're approaching a third from above, so that means we're approaching and bending like that. And that's enough detail for this portion of the graph. If you have the two end behaviors, connect them, and you're good to go. That leaves us with one behavior, and that behavior is right here as we approach f of x as x approaches negative infinity. It looks like we're going to approach from below, but let's do a quick test to verify. X, f of x. We're going to plug in large negative numbers like negative 1,000 and negative 1,000,000, and we get 0.332 and 0.33332. Numbers that are slightly less than 0.33333, so that means we're approaching from below, which matches the rest of our graph. So that is a full analysis of how to graph a rational function, from starting with asymptotes and discontinuities, following through with x and y intercepts, and then plugging in numbers to find the behaviors around vertical asymptotes and around horizontal asymptotes. Okay. Do you have to show your work for when you're plugging in large values of x and large negative values of x? No. This is an optional portion of your analysis. Do you have to plug in the summary? Yes. By plug in, do write down. You have to write down this summary? Yes, you do. Just like you have to write down this summary. In fact, you could merge the two tables and say as x approaches infinity, f of x approaches a third from above, negative infinity, a third from below. And that would be an acceptable way to conclude. Okay, so one last time, let's look at what we've got here. We factored first to see if we had a hole. We did not, so we concluded there was no hole. Since we have a restriction in the denominator and it's not a hole, it means it's a vertical asymptote. Any restriction on the denominator will be a vertical asymptote if it remains and can't be divided away. Since the degree of the top and bottom polynomials were equal, means we have a horizontal asymptote. Since they were equal, we take the ratio of the coefficients on x to find out what the horizontal asymptote is. If the degree of the numerator was bigger, if the degree of the denominator was bigger, we would have a horizontal asymptote at 0. If the degree of the numerator was bigger than the denominator, we'd have to do polynomial division and look for an oblique asymptote. In this case, we had a horizontal asymptote. Once we found our discontinuities, our next step was to find our x-intercepts by making y0, to find our y-intercept by making x0, plot them on our graph, along with our asymptotes. And then the last step is to find the behaviors around the asymptotes. To find the behavior around the vertical asymptote, you plug in a number slightly to the left of 2, slightly to the right of 2. If the number you get out when you plug in a number slightly to the left is negative, it means we're approaching negative infinity. If the number you get when you plug in is positive, it means you're going to approach positive infinity. Because as you approach a vertical asymptote, you have two choices, up or down. If it's positive, it's going up. If it's negative, it's going down. Horizontal asymptote, once you figure out it's a third, to figure out the behavior, plug in one really large number. You don't have to plug in 2. Plug in 1,000,000 and see what you get. If you get a number that's slightly over or bigger than your horizontal asymptote value, it means you're approaching from above. If you get one that's slightly less, like this one was 0.332, our asymptote says 33333, so 2 is less than 3, which means you're approaching from below. That's what that designation is, the negative, from below. So that means you're approaching your asymptote from below as x approaches negative infinity. And that's a full key features analysis of a rational and graphing it from a full analysis. Your assignment will be just like this, except your rational will be significantly bigger. There'll be more factoring involved, there'll be multiple holes, and there'll be a vertical asymptote or 2, because you could have multiple restrictions on the denominator, and you'll have to look at all your behaviors around both or more than one vertical asymptote. You could have a horizontal asymptote, you could have an oblique asymptote, and you have to look for the behaviors around that, just like we did here. The beautiful part is that the way you do a question like this doesn't change. It's always the exact same. The analysis looks exactly like this every time. The way you interpret it dictates what your graph's going to look like. That's it for part 1. In part 2, what I ask you to do is compare these 3 functions by graphing them in Desmos and seeing what changing that last value does to the graph and come up with a conclusion. Same for changing the d value, which is the number in the denominator. See what that does to your graph and come up with a conclusion. And then we're going to pick right back up for part 2 of the videos, where we're going to summarize what happens when you have rationals in this form and how you can graph your rationals quickly using key features. Thanks for watching.